Hello and welcome to another Flip Classroom lecture. This one is on projectile motion. Now just to get us oriented, just want you to recall our equations of motion. I have the acceleration equations listed right here. There are four of them, and there's the constant velocity equation right here. This is a simpler version, just essentially distance equals rate times time, or x equals vt. We're going to be using these. Now, let's think about what happens to a ball when it's flying through the air. Gravity is acting on it. That's the only force that's acting on it, and it's pulling it downwards. It's always pulling it downwards, so the ball will always accelerate downwards. Projectile motion confused people for a very, very long time, and it was pretty much Galileo who figured out what was going on, and his big insight was that the horizontal motion and the vertical motions of the ball are two separate and independent motions. And he correctly reasoned that horizontally the ball was just moving along at a constant velocity, and vertically it was accelerating down due to gravity. And you put those two motions together and you've got projectile motion. And I believe that that's what you saw in the lab, that horizontally it was constant velocity and vertically that it was accelerating downwards. We're going to be focusing now on a more specific kind of problem, and that is the horizontally launched projectile. And we're going to focus on this problem because this one's fairly somewhat straightforward to model mathematically. And this is one where a projectile is launched straight out horizontally and just falls in this path here. Think of a marble rolling off a table, or in basketball, somebody passes the ball and they pass it straight forward without any up or down angle. Now, let's review what we know about projectile motion. Horizontally, this thing is going to be moving at a constant velocity, and it should look something like this. It should just be moving merrily along at a constant velocity. If we like in Logger Pro, if we each successive frame, the ball will have traveled the same distance. And we can model it with this equation, x equals vt, our equation for constant velocity. Vertically, it's doing something very different. Gravity's pulling it down, so it's going to be accelerating. And if we were to go frame by frame in Logger Pro, it would look something like this. It would start right here, and then one frame later it'd be here, another frame later here, and then here, and then here. Its spacing gets bigger and bigger because it's going faster and faster and faster. Now, how are we going to model that mathematically? We'll start with this equation. It's one of our acceleration equations. We know, since it is launched horizontally, that its initial velocity up or down, remember we're just looking at the vertical motion here, just looking vertically, its initial velocity up or down is 0. So this term simply goes away. And then we've got x equals 1/2 at squared. And calling the vertical motion x is terrible. Let's call it y. And this will remind us of an xy axis, where the x-axis is horizontal and the y-axis is vertical. So we'll call this position y to remind us that it's vertical. And then we have this equation right here for the vertical motion, just y equals 1/2 at squared, where a is the acceleration due to gravity. Okay, let's put this all together. In projectile motion, you've got something moving in two dimensions. We could consider the horizontal and vertical motion separately, and this is what it should look like if you were looking at it in Logger Pro. One frame, next frame, next frame, next frame, next frame, and the equations you'd model this with are x equals vt, that's the horizontal motion, that x is horizontal, and vertical, it's y equals 1/2 at squared. And voila, we've got our mathematical model, and then we can go and do cool things like predict where stuff was going to land and how long it's going to be in the air and all kinds of neat things like that. So let's just talk about how to do that, because it's a little different than what we've seen. So here's a pretty vanilla sample problem. A marble rolls off of a table. The table's 1 meter high. The marble's moving at, say, 3 meters per second. How far away from the table will it land? This is a pretty standard problem in projectile motion. I can change the numbers around. Maybe it's not a table, maybe it's a cliff, and whatever. And I put the equations here to remind you of what they are. So we're good problem solvers. We know where to start. We draw a diagram. I've already provided that right here. We write down what we know. I'll write it down here in the diagram. We know the velocity of which this marble's launch is 3 meters per second. We know that the y, the height of the table, is the y, which is 1 meter. The acceleration should be 10 meters per second squared because presumably we're on Earth. I'll call down the positive direction so I can make this positive. If you put it and make it negative, it's not going to make any big difference. And we like to figure out x, which is the horizontal distance there. So that's what we're looking for. All right, so which equation should we use? Well, the one with x in it. Come on, this is really obvious. So here we go, x equals vt. It's the only one with x in it. We know what our v is, and t. What the heck is t? T is the time that it's in the air, and we have no idea what that is. So should we just give up and despair? Is this unsolvable here? Has Mr. Chipkin given us a problem that cannot be done? No. Some of you might have already seen that we can solve for time using the second equation right here. We know what y is, it's 1 meter. We know what the acceleration is, it's 10. We can solve for t, and once we solve for t, we can plug it in the first equation and get our answer. And you can go ahead and try this one here, and yeah, I'll see you in class. Have a good evening.